To sustain the global food supply and maintain the crop yields that keep billions of people alive, human agriculture relies heavily on urea fertilizer. But manufacturing that fertilizer comes with an enormous energy penalty. The conventional industrial processes used to produce urea consume roughly 2% of our total global energy every single year. That massive energy draw translates directly into climate damage. Traditional production facilities release over 200 million tons of carbon dioxide into the atmosphere annually. We are trapped in a destructive loop. The primary method we use to feed the planet is heating it, which means we require an alternative way to synthesize this chemical. Chemists have a potential alternative. By using low-carbon electricity, they can run an electrochemical reaction that fuses captured carbon dioxide and nitrate waste directly into urea. In a small laboratory setting, this process works. However, for industrial factories to be economically viable, they must operate at high production speeds. For this method to reach commercial scale, a facility needs to maintain a continuous production rate, or current density, of exactly 100 milliamps per square centimeter. This requirement is where the engineering fails. When scientists increase the power to hit that production threshold, the catalyst driving the reaction begins to break down. The high power triggers unwanted side reactions. Instead of binding carbon and nitrogen together, the system starts producing hydrogen gas, making the process too inefficient for use. It is a scale-up paradox. The clean alternative works, but only when it runs far too slowly to ever replace our current industrial methods. To bypass years of physical trial and error, researchers at the National University of Singapore used large language models to map out the scientific bottleneck. They fed AI data from previous studies to identify why the chemistry fails at high speeds. The analysis pointed to iron oxide. It showed promise as a base material because of its ability to activate the required nitrate molecules. To refine that material, the team utilized density functional theory. This involves advanced quantum simulations that allow researchers to virtually test how molecules behave on a surface before building it in a lab. The simulations generated a specific structural change, introducing cadmium directly into the iron oxide base. Adding cadmium was a digitally calculated specification, explicitly designed to solve the high-speed scaling problem. At the catalyst's crowded surface, molecules compete to attach. Unwanted carbon monoxide and hydrogen stick too easily, blocking the reaction. Cadmium alters the electronic structure, forcing these molecules to detach. The cleared catalyst then links carbon and nitrogen to form urea. The cadmium effectively acts as an atomic traffic cop. By repelling the side reactions, it ensures the process can run at high speeds. After the simulation, the researchers returned to the laboratory to synthesize the cadmium-modified catalyst and test it against real-world metrics. This chart compares catalysts against the requirement of 100 milliamps per square centimeter. Most failed to reach this industrial minimum. The new catalyst exceeded that target, maintaining a continuous current density of 140 milliamps while converting over half the electrical charge into urea. The reaction was also durable, demonstrating stable performance over 100 hours of continuous operation. For the first time, a clean fertilizer production method has proven it can survive the high-volume demands of factory-scale operation. This urea breakthrough highlights a broader change in the fields of chemistry and materials science. Artificial intelligence and quantum simulations are no longer just used to explain why an experiment worked after the fact. Instead, AI can now identify the correct design principles from the beginning, allowing researchers to skip the trial and error phase. This method provides a direct route for identifying the parameters needed for other sustainable chemical transformations, using algorithmic specifications to build the materials required for a more sustainable future.